Well, now that we have the basics of indefinite integration under our belts, it's time to start looking to see, well, how would we do this in general? Rather than taking an example as we have so far, where we differentiate a function and then just kind of make a deduction about an indefinite integral from that, if I was to take a function and just say, well, what's the indefinite integral of this function, what process would we follow? And so far, it looks like the most reasonable way to proceed is going to rely on those differentiation facts that we established in Math 1000. And so therefore, the general process we used for differentiation hopefully will serve us pretty well for integration as well. And remember, for derivatives, the three basic steps were, first of all, if necessary, take the function we were given and rewrite it in a more convenient form. Secondly, apply the differentiation rules. And thirdly, perform any obvious simplifications. So let's kind of turn that around for the purposes of integration. So the general process for indefinite integration, then, is as follows. And again, it's going to be a three-step process. And well, if we're going to want to try to make use of our differentiation results and basically just turn them around, the first thing we're going to need to be able to do is to recognize the function that we've been given as something familiar. So again, rewriting the given function, if necessary, is going to be a very useful step. So we're going to rewrite the integrand in a more convenient form, if necessary. That won't always be a requirement, and frankly, it won't always be possible, but sometimes it's going to be very, very useful. Once we've done that, then we want to try to use our knowledge of differentiation to make an appropriate deduction about what the indefinite integral must be. So then we'll identify the indefinite integral based on our knowledge of derivatives. And this is why having a really good handle on all of those rules and facts about differentiation from Math 1000 is so very, very intrinsically important here in Math 1001. And then once we've done that, of course, we may have an opportunity to simplify. And so obvious simplifications, as I talk about in Math 1000, if you took that course with me, that's a little bit subjective, but we're talking about, again, things that don't take a whole lot of work. If you've got two constants that are being multiplied together, multiply them together. If you've got two like terms that are being added together, if you've got, say, 5x squared plus 7x squared, add them together to get 12x squared. If there are any really obvious trigonometric identities that you could apply to simplify, to cancel some terms, or something like that, then that's a useful thing. Similarly with properties of logarithms or finding common denominators. But if it's not obvious that the use of those things is going to make your result nicer, make it simpler, then you don't need to worry about that kind of thing. So these really should be things that just immediately jump out at you. That's the kind of simplification we're looking for. So we'll perform any obvious simplifications if possible. Because sometimes there aren't. Or sometimes they're not obvious. So for example, let's suppose I wanted to find the indefinite integral of the function 5 times x to the power of 9 over 2 all over the square root of x. at first glance, this seems like a really hard problem, because the only way we could do this up to this point, 25 minutes into Math 1001, would be to be able to come up with some function that when we differentiate it gives us 5 times x to the power of 9 over 2 divided by the square root of x. And that's probably isn't right on the tip of your tongue. I don't blame you. But this function can certainly be rewritten. We can rewrite the integrand. Because in particular, remember, a square root of x is also a power of x. That's also the same thing as x to the power of a half. And if I've got x to the 9 over 2 divided by x to the half, laws of exponents tell me that I can subtract those powers. So that's really going to be the same thing as 5 times x to the power of 9 over 2 minus a half, which is 8 over 2. So that's x to the power of 4. All right, so now we can ask the question, do we know any functions that when we differentiate them give us 5 times x to the 4th? And hopefully that comes to mind a little bit more readily, because yes, we do. That comes from the power rule again. From the power rule for derivatives, well, we would know that the derivative of x to the power of 5 is 5 times x to the 4th. So then the integral of 5 times x to the 4th, that's going to be x to the 5th. And again, don't forget the plus c. And so that's the answer we're looking for. You might ask, well, why leave it in that form? Why, or I guess more to the point, why choose x to the 5th as the antiderivative that we stick in here and add the c to? If there's really an infinite number of antiderivatives, would it be wrong to write the answer here as x to the 5th plus 1 plus c, for example? And while that would be a true statement, that wouldn't be a completely simplified answer. Because if we did have x to the 5th plus 1 plus c, well, we have to remember that c represents any real number. And if I've got a plus 1 plus any real number, well, if you add 1 to any real number, that's still any real number. So we could simplify that to x to the 5th plus a new constant integration, which you might call d or c1, or often you just see c reused, even though it technically means something slightly different now. So what we're going for when we're doing indefinite integration is almost always going to be the simplest antiderivative, the antiderivative that doesn't have any constants added or subtracted to it, because we're always going to tack on that arbitrary constant, that plus c, at the end anyways, which takes care of all of those constant terms. All right, so that's our general process for indefinite integration. But of course, because we're relying on our knowledge of differentiation, it's not always going to be obvious which differentiation rule is going to apply in any given situation. And it also means that we're going to be able to come up with lots of situations where those differentiation rules will not directly apply. And we're going to need to think about, well, what do we do in those situations? So to make our lives a little bit easier here, I think what's a useful first step in getting used to this whole concept of indefinite integration is to go through all of those differentiation rules that we learned in Math 1000 and basically turn them around and turn them into equivalent rules for integration. So we can use our results for derivatives to establish several what I'm going to call common integrals. These are integration results that we're going to come back to again and again and again. So it's going to be really, really important to commit these to memory, and to just have these as facts right on the tips of your fingers, so that you're when you need to make use of one of them, it's going to be right there. It's going to be automatic. You're going to be able to put it down. So how are we going to come up with this list of common integrals? Well, probably the most sensible thing to do is start with the simplest differentiation rules, turn those into integration results, and then build up to our more complicated rules or our slightly more obscure functions as we go along. And with that in mind, then, well, what's the simplest differentiation rule that we've got? Well, I've already made reference to it today. It's the constant rule. It's this idea that if we differentiate any constant, the derivative is always zero. So the first common integral then, turning that around, would be to say that, well, if I've got the integral of 0, well, what functions differentiate to give me 0? It's simply the derivative of any constant. So the integral is just that arbitrary constant, that constant of integration, c. Pretty simple, but it's always good to start with 0 and know how that works before we go on to anything more substantial. Right, well, what's the next most complicated differentiation result we've got? Well, that's the derivative of x. We know that the derivative of x is 1. So if I wanted to integrate 1 dx, which, by the way, you'll often see written, because of course 1 times anything is the anything, you'll often see that written as just the integral of dx, with the 1 hidden, basically. It's kind of redundant to actually write it out. So the integral of 1 dx, or the integral of simply dx on its own, well, the derivative of x is 1, then the integral here is x. But again, don't forget, plus c. That constant of integration always has to appear in any indefinite integral. There's 2 common integrals. Let's do some more in the next video.